Hi everyone, my name is Michael, and today I'll be presenting our work on experience selection using dynamic similarity for efficient multi-source transfer learning between robots. This is joint work with Siqi Zhou and our supervisor, Professor Angela Schoellig at the University of Toronto. Robots are operating in increasingly complex environments, such as drone delivery, as shown here on the right, in which they're subject to unmodeled dynamics, such as variable payloads, or unmodeled disturbances, such as wind. These uncertainties in dynamics can limit the performance of model-based control techniques. One approach to deal with this challenge is to collect data from the robot and use learning to improve performance. However, data collection can be expensive or time-consuming. If we've already trained on one robot, is there a way that we can reuse this existing experience? And this is the goal of transfer learning, in which we seek to leverage existing experience to accelerate or improve subsequent learning. In robotics, transfer learning has two approaches: cross-task transfer and cross-robot transfer, which is what we focus on in this paper. So some common approaches to cross-robot transfer are alignment-based transfer, in which we learn a map from source robot data to target robot data, and invariant feature learning, in which we identify features that are common between the source robot data and target robot data. Previous work in our lab has shown that we can transfer an inverse dynamics module from a source quadrotor to a target quadrotor to improve the target quadrotor's trajectory tracking. The baseline tracking error performance without transfer is shown here in gray over 10 trajectories, and shown here in green is the tracking error when we transfer the inverse dynamics module, which we see reduces the tracking error. And the tracking error is further reduced when we collect a small amount of data online while doing this transfer, which is shown here in blue. While there's many approaches in the literature to achieve successful transfer learning, one question that's less often analyzed is the similarity between the source and the target robots. Transferring experience from a source robot that's dissimilar to the target we won't expect to work well. Which is the research question that we analyze in this paper, is how can we analyze similarity between robots for safe transfer learning? Our contributions are threefold. We propose an approach for characterizing the similarity between robots based on the new gap metric from robust control. We introduce an experience selection algorithm based on the similarity characterization for efficient transfer between robots whose dynamics are possibly unknown. And we demonstrate the proposed similarity characterization with quadrotor experience transfer experiments. From robust control, one notion of distance between two systems is the new gap metric. And inspired by this, we propose a characterization of robot similarity that we can estimate from simple periodic experiments on the source and target robots. We characterize similarity based on the input-output response of the source and target robots to periodic inputs with the frequency omega, which for a linear system, you recall for a particular frequency, can be characterized by a complex number z of omega, which is in terms of the amplitude gain, the ratio of the output shown here in blue and the reference shown here in red, and the phase shift, which quantifies the time delay from the reference to the output shown here at the bottom. We compute the similarity between target robot RT and a source robot RS based on the chordal distance between the respective input-output responses, ZT and ZS, when projected onto the Riemann sphere. We can plot these 2 points in the complex plane and project them onto the Riemann sphere in gray, shown here, where the projections are shown with open red dots and open blue dot, respectively. If we zoom in on these projections, the chordal distance between ZT and ZS is simply the Euclidean distance between their projected points, which we can measure using this function, psi, whose expression is given below, called the chordal distance. We characterize similarity between a target robot RT and source robot RS over a frequency operating range W that's feasible for the robots to track. We characterize it based on the largest or the worst case chordal distance, and we denote the similarity characterization by psi star. And it holds that psi star is bounded between 0 and 1, and is equal to 0 if and only if the input-output responses ZT and ZS are identical. So as a result, we interpret values of psi star being closer to 0 as indicating that the source robot RS is more similar to the target robot RT. So, given n source robots, RS1 through RS capital N, we select experience from the source system most similar to the target, namely the system with minimum psi star n, where psi star n denotes the similarity between the nth source robot to the target. Formulating experience selection in this way, we see gives us a minimax optimization problem. And we can solve this optimization problem using Bayesian optimization. In particular, we model each objective function, psi n, with a Gaussian process with posterior mean psi n hat and posterior variance sigma n hat squared, and we find its maximum through iterative sampling. We start with an initial sample, denoted by omega sample, and we perform periodic experiments on the source and target robots by sending a periodic trajectory with frequency omega sample and observing the input-output response of the source and target robots. We can compute Zt, Zsn, and psi n of omega sample. From this data, we fit each new GP, psi n hat, with the new samples, an example of which is shown here on the right, where we have 3 GPs, which are shown with the green, blue, and yellow curves, where the shaded regions are the 3 sigma bounds. Once we refit the new GP, we compute a new sample location based on an acquisition function that encourages selecting samples at points at the worst case chordal distance for more similar robots. So in this example, the next suggested sample is on the right-hand side of the plot, denoted with the red dotted line. Once we have this new sample location, we perform more periodic experiments, computing psi n of omega sample. We refit the new GP with this new sample and compute a new sample location, shown here with the red dotted line. Upon convergence, our estimate of similarity between the nth source robot and the target is given by psi n hat star, which is the maximum of the GP posterior mean, which is shown here with the black crosses on each plot. And we select experiments from the robot that's most similar to the target, namely the one with minimum psi n hat star, which in this case is source 2, the yellow curve. We test our similarity characterization with an inverse module transfer problem, in which we have a target robot equipped with its own baseline controller, shown here in gray. We pre-cascade an inverse learning module, shown here in green, with the goal of achieving an identity map between the desired output YD and the actual output YA. We represent the inverse dynamics of the target robot using a Gaussian process, and we embed the inverse dynamics of a source system as the prior mean of this GP. In our experiments, we have 5 source systems. First is the Crazyfly 2.0 quadrotor, the Crazyfly simulator, the Parrot AR-Drone quadrotor, the AR-Drone simulator, the Parrot Bebop quadrotor, and we have 1 target quadrotor, the Crazyfly 2.0 heavy. And we demonstrate our approach, tracking hand-drawn test trajectories, such as the ones shown here on the right. Our first set of experimental results is this estimation of similarity between each source robot to the target. Running our iterative BO algorithm, we obtain convergence after 9 iterations. And here we plot the PDF corresponding to the similarity estimate, with PDS closer to 0, indicating that the source robot is more similar to the target. The most similar source to the target is source 1, followed by sources 2, 3, 4, and 5. From this plot, we expect that using the inverse module from source 1, the most similar quadrotor to the target, should give the best transfer performance. And indeed, this is what we observed in our experiments. When using an inverse module from source 1, we achieved the highest RMS error reduction relative to the baseline tracking performance of the target robot without any transfer. And we observe a general correlation that using the inverse module from more dissimilar source systems gives worse transfer performance, which is made even more evident as we increase the speed of the trajectory, making it more aggressive. Here's a short video using the inverse module from source 1 on a hand-drawn trajectory. The plot on the left shows the desired trajectory as the red dotted line, with the actual position of the quadrotor in blue. And on this trajectory, we had a RMS tracking error of 4 centimeters. To sum up, we presented a characterization of similarity between 2 robots, and we proposed an experience selection algorithm based on this similarity characterization. Lastly, we demonstrated transfer from the most similar source quadrotor led to the best transfer performance on the target quadrotor. Thanks for watching.